On June 28, 2009, Stephen Hawking threw a party. He had champagne, balloons, canapés laid out on the table. He sat in his wheelchair in the decorated room for hours. Nobody came. Not one person. Why would you throw a party and invite nobody? Who are the guests supposed to be? What does an empty room prove? Can you actually prove something doesn't exist just by waiting for it? Everyone says time travel is impossible. But how do you know? You can't just declare it. You need evidence. Hawking designed an experiment that turns absence into data. The empty chair becomes the answer. Here's what makes it brilliant. He sent the invitations afterward. The party happened first. Then, only after it was over, Hawking published the coordinates. June 28, 2009. Specific location in Cambridge. Exact time, 12 count Universal Time. He included the latitude and longitude. The only way you could have attended was to travel backward through time. If time travel to the past ever becomes possible, in the year 3000, year 100,000, doesn't matter when, anyone in the future could read those coordinates, step into their time machine, and arrive at that party in 2009. Hawking sat there. I sat there a long time, he said. Nobody showed up. So does that prove time travel is impossible? Well, maybe they just didn't want to come. Maybe time travelers did arrive but stayed hidden, watching from outside. Maybe the coordinates got lost over thousands of years of changing languages and forgotten archives. Maybe there are rules, time traveler ethics, about revealing themselves to primitives like us. Hawking knew all these objections. I was hoping at least one of them would come, he said. But here's the thing about proof by absence. Some absences tell you nothing. Nobody sitting on a random park bench at 3 a.m. doesn't mean people don't exist. But some absences tell you everything. No working perpetual motion machines in the patent office tells you perpetual motion violates physics. What's the difference? Theoretical possibility versus physical law. Actually, this experiment is more clever than it seems. If time travel to the past is possible, even once, even somewhere in the entire future of the universe, then someone eventually should be able to reach that party. We're not talking about whether your neighbor builds a time machine next Tuesday. We're talking about potentially millions of years of future civilization. Maybe billions. All of future humanity, or whatever comes after humanity. All that time, all those minds, all that technology. Somebody, somewhere, somewhen should have wanted to visit Stephen Hawking's famous time traveler party. It's documented. It's permanent. It's become part of history now. The coordinates are published. The invitation stands forever. Nobody came. Which means either they can't come or something prevents it. Let me show you why backward time travel is different from forward. Going forward in time is easy. You're doing it right. Now, 1 second per second. You can do it faster. This is proven. Move fast enough or get close enough to strong gravity, and your clock slows down relative to others. Astronauts on the International Station age slightly slower than people on Earth. Atomic clocks flown in airplanes tick slower than clocks left on the ground. This isn't theory. We measure it. You experience less time, you arrive in everyone else's future. That's forward time travel. It works. Going backward is where physics gets uncomfortable. Why? Causality. You arrive before you leave. You could prevent your own departure. The grandfather paradox sounds like philosophy, but it's geometry. Space-time isn't like space. It has a direction. Entropy increases. Effects follow causes. To travel backward, you'd need closed time-like curves. Paths through space-time that loop back on themselves. Do such curves exist? In 1949, Kurt Gödel found something disturbing. He was Einstein's friend, a logician, and he found an exact solution to Einstein's field equations. A rotating universe. If the universe rotates, space-time itself twists. Travel far enough in one direction, follow the twist, and you come back to your own past. Not metaphorically, literally. Same event, same moment you left. Einstein was disturbed. He thought such solutions should be excluded on physical grounds, even though they were mathematically valid. Then in 1963, Roy Kerr found another, rotating black holes. If a black hole spins fast enough inside the ergosphere, the region where space-time itself is dragged around, paths can loop. In principle, you could enter, travel on a closed time-like curve, exit in your own past. Problem? You'd be crushed by tidal forces, or you'd need exotic matter with negative energy density to hold the path open. But mathematically, time travel to the past isn't forbidden by general relativity. It's allowed in the equations. So why doesn't it happen? This is where Hawking's theoretical work comes in. In 1992, Hawking proposed what he called the chronology protection conjecture. The universe, he suggested, has a built-in mechanism that prevents time travel to the past, not in the equations of general relativity, in quantum effects. Here's how it would work. Imagine you have a wormhole connecting two times, present and past. A particle could go through, loop back, return to its own past. But quantum field theory says the vacuum isn't empty. It's seething with virtual particles, popping in and out of existence. These virtual particles would travel the loop. They'd accumulate, build up. Positive feedback. The energy density at the wormhole throat would approach infinity just as the wormhole becomes a time machine. The wormhole destroys itself. The universe protects causality. Hawking joked about making the universe safe for historians. Curiously, this isn't proven. It's a conjecture. The calculations are incredibly difficult. Some solutions suggest it works, some don't. The jury's still out. We don't have a complete theory of quantum gravity to settle it definitively. So the party was testing this in the only way you can, by waiting. The party date was carefully chosen, well documented. The champagne was really opened. The room was really prepared. Photographs exist. The coordinates were published in multiple places. There's a permanent record that the invitation existed. And now the waiting has begun. Not just for that one day, forever. Every day nobody shows up is more data. If civilization lasts 1,000,000 years and develops time travel, someone should show. If 1,000,000,000 years pass with no visitors, that's stronger evidence. The empty room compounds. Each year of silence adds weight. This isn't a philosophical argument. It's observational data. Accumulating evidence for chronology protection, or evidence that civilization doesn't last long enough, or evidence that time travel to the past never becomes possible for any species anywhere. All three possibilities are interesting. All three tell you something about the universe. Which brings us back to why backward travel might be fundamentally different from forward. Forward time travel is proven. Astronauts age slower. Atomic clocks in fast-moving planes run slower. Fast motion or strong gravity slows your clock relative to others. You experience less time, you arrive in their future. This works because you're taking a shortcut through space-time, a more efficient path. You're not violating causality, you're just taking the quick route while others take the long way. Backward travel would require different topology entirely. Space-time would need holes, bridges, closed curves that loop back on themselves. Or you'd need the entire universe to be rotating, dragging space-time into a twist. The problem isn't energy or technology. The problem is the structure of space-time itself and something deeper, thermodynamics. The second law, entropy increases. Broken glass doesn't spontaneously reassemble. Smoke doesn't flow back into the candle. Heat doesn't flow from cold to hot on its own. This isn't just probability. It's time's arrow. The universe has a direction built into its physics. Now, if you travel backward in time, you'd be moving against the entropy gradient. Your own body, your cells, your brain, your atoms. Entropy increasing as it must. But the universe around you would be running backward. Entropy decreasing. Broken glass assembling itself. Smoke flowing back into candles. creates a contradiction at the boundary between you and everything else. Some physicists think this prevents backward travel fundamentally. Others think maybe at the quantum scale, before decoherence kicks in, before you're entangled with the environment. Maybe there's wiggle room for closed time-like curves. But macroscopic objects, people, spaceships, anything big enough to carry information are too entangled with their environment. Would require reversing the entropy of a huge region of space-time just to let you pass. The energy cost might be astronomical, possibly infinite. So what did the empty room actually prove? Not absolute proof that time travel is impossible, but strong evidence it never becomes practical. If it were possible and practical, someone should have come. The future is long, millions of years potentially, billions. Curiosity seems to be a persistent trait in intelligent species. Hawking's invitation is permanent, documented, famous. Nobody came. 3 possibilities. First, time travel to the past is impossible. Chronology protection works somehow through quantum effects we don't fully understand yet. The universe won't allow closed time-like curves to form or won't allow macroscopic objects to traverse them. Second, civilization doesn't last long enough to develop it. We're filtered. Some great catastrophe ahead that prevents any species from reaching time travel capability. Third, it's possible, but so difficult, so expensive, so dangerous that nobody ever does it. Not even once. Not even as a stunt. Not even to meet Stephen Hawking. Any of these 3 is significant. The first means the universe has a deep protection mechanism built into its laws. The second means there's a great filter ahead of us, something that stops technological civilizations. The third means there are fundamental limits we haven't discovered, boundaries beyond which even far future physics can't go. Hawking preferred the first interpretation. It seems there is a chronology protection agency, he said, which prevents the appearance of closed time-like curves and so makes the universe safe for historians. The universe is self-consistent. It won't allow paradoxes. Causality stays intact. But here's what's chilling about the experiment. The party was in 2009. Hawking died in 2018. He's gone. But still nobody has come to the party. The invitation still exists. The coordinates are still published. If time travel becomes possible in the year 3000, they could come to the 2009 party. If it becomes possible in the year 100,000, they could still come. If it becomes possible a million years from now, after humans are extinct, after something else evolves, after that species discovers our archives and reads about Hawking's party, they could come. The experiment is still running. It will run forever. Every year of silence is more evidence, but it can never be complete proof. Maybe someone shows up tomorrow. Maybe in 1,000 years, someone appears in that room and nobody's there to witness it. Maybe the invitation sits waiting for 10 million years before someone finally arrives. The room is empty now. That doesn't mean it stays empty forever. This is what makes it chilling. We're not waiting for the answer. We're in the waiting itself. The experiment has no end date, only ongoing absence, a growing mountain of non-events. Each silent June 28th that passes is another data point, proof by infinite patience, which means we'll never know for certain. Not in our lifetimes, not in our species' lifetime, probably. The experiment outlasts the experimenter. It's designed to. Maybe it outlasts our entire civilization. And that's the point. Hawking knew he wouldn't see the conclusion. He didn't need to. The absence itself is data, accumulating year after year, each silence slightly more suggestive than the last. He sat there for a long time, he said. In a sense, he's still sitting there. The empty chair is still waiting. The champagne has long since gone flat, but the invitation is permanent. The coordinates, 52.2 degrees north, 0.1 degrees east, June 28, 2009, 12 Universal Time. A standing invitation to anyone, anywhere in the future, who can bend space-time backward and navigate to that moment. So far, silence, which either means they can't come or they chose not to, or we're still early in the experiment. Next question. What if someone does show up 50 years from now, and we miss it because nobody's watching? That's a different problem. I gave a party for time travelers, Hawking said. Nobody came. Still true. For now.